Olá, gente. I'd like to ask if are there any foreigners here for starting? She left. Really? So we better to present in English. Really? Okay then. So I'm Fabiano, and I'm going to present my work entitled Characterization of proteases from Bacillus licheniformis and optimization of Xantomonas campestris lysis using response surface methodology. This is part of my PhD thesis, and currently I'm doing the PhD in the Brazilian Bioethanol Science and Technology Laboratory. And here's my email if you want to contact me. Okay. Alright, so I will start talking about proteases. They are enzymes capable of hydrolyzing peptide bonds. They act in mild reaction conditions with no need of cofactors. And they can be produced by bacteria, fungi, and yeasts. They are the most used enzymes, representing 60% of the enzyme market, and they present several industrial applications. For example, in food industry, they are used for cheese manufacturing for the obtainment of cheese with different aromas, bakery products for the obtainment of bread with different texture, for the obtainment of bioactive peptides through hydrolysis of proteins, in this case, peptides that present antioxidant activities, some therapeutical activities. They can be used in pharmaceutical industry, for example, as components of medicines like pancreatine, and they are used in organic synthesis for the obtainment of therapeutical compounds, including some bioactive peptides as well. They are used in textile industries for the obtainment of leather to remove some residues of proteins. But the major application of proteases in the detergent industry, they are part of detergent formulation, but in this case, they must be stable in surfactants and some other compounds that can inactivate these proteases. And they are used because they are capable of removing protein stains, like, for example, in blood, which is quite hard to remove without the help of enzymes. And one very interesting application of these enzymes is in the clarification of xanthan gum. Xanthan gum is a food additive that is used as a thickener. They can control viscosity of several food products. And this gum is produced through the fermentation of some sugars using Xantomonas campestris. But for some applications, it is necessary to remove cells from the fermented media containing the gum, and in this case, there are several methods, but they can present disadvantages. For example, the degradation of the gum, like changing the pH, or centrifugation, but in this case, you need to dilute the gum, which is not good for this purpose. So one alternative is using proteases, because they can degrade the cells by degrading the proteins in the cell wall, like peptide glycan, resulting in the removal of the cells. So we have the clarified gum. Regarding the protease production, Bacillus is an important genus of microorganisms producers of extracellular protease, and they can frequently produce proteases with high activity, alkaline proteases, which is quite good for the application in the detergent industry, thermostable proteases, and proteases stable in the presence of detergent compounds and organic solvents. These enzymes are produced by these microorganisms through or under submerged fermentation. In this case, we use proteins as inducers, like casein, yeast extract, peptone, and this is the classical method and more used for industrial production of enzymes, and it is very interesting to consider using agro-industrial wastes and byproducts or residues as well then we can reduce the cost of the production. In this case, we can use sugarcane molasses, corn staple liquor, and etc. Now we will talk about specifically this work, some experimental parts, and combined with the results. In this study, we used a Bacillus licheniformis strain, and the enzyme was produced in a medium composed of sugarcane molasses, corn staple liquor, yeast extract products, Slaca, dry whey, and the enzyme was produced after incubation for 4 days, 30 Celsius degree, and 200 RPM. So we then separated the cells, and we obtained the crude enzymatic extract. We discarded the cells, and we obtained the crude enzymatic extract. But we also evaluated the purification of this enzyme, and then we started with precipitation with ammonium sulfate, and then dialysis, and then we removed the water with lyophilization, and then we used gel filtration using Cifadex G100. Dilution was performed using phosphate buffer, pH 7 and flow of 0.3. And then we have here a dilution of proteins and protease activity, and we can observe the protease activity and dilution of the proteins. This fraction here was used to carry out all the experiments with the partially purified protease. And we obtained a purification fold of 3.69. All right. So, and then we characterized these two protease preparations, the crude enzymatic extract, and then the partially purified protease. And we used the CCD, a central composite design, to optimize this process. And we evaluated the pH and temperature of activity. The pH was from 5 to 10, and temperature from 30 to 80 Celsius degree. And then we also evaluated the stability of the enzyme in different pH values and temperatures. But in this case, first we incubated both preparations in these conditions. So pH, we varied from 5 to 10, and temperature from 30 to 70. And we can observe here that the profile of the activity of both preparations were very similar, with optimal conditions at 55 Celsius degree and pH of 7.5 for both preparations, crude and purified. And regarding protease stability, we can observe again similarities between the two preparations, crude and the purified, and we observed good stability. 95% of residual activity after incubation of 1 hour in the pH range from 5.7 to 9.3 when the temperature was 30 to 36 Celsius degree. Now regarding the clarification of xanthan gum, the Xantomonas campestris was fermented in a medium composed of sucrose, peptone, some salts, and initial pH of 7. We prepared a pre-inoculum that was fermented for 24 hours and 28 Celsius degree, and we used 10% of this as inoculum to produce the gum, but now for 72 hours. And then after the production of the gum, we had the fermented medium with the xanthan gum and the Xantomonas campestris cells. We evaluated the lysis of these cells. So we diluted the fermented medium, and then we diluted in water, and then we applied in Erlenmeyer flasks of 125 milliliters. We used 10 mLs, And we evaluated different concentrations of protease in different temperatures. We used for that response surface methodology. And we determined the increase of transmittance, which is we use to indicate the lysis of the cells. For that, we used again a central composite design. We varied. In this case, we used for protease concentration, we used unit of proteases per ml of cell suspension. It varied from 9 to almost 50, with slightly differences for crude and partially purified protease, and the temperature from 30 to 70 Celsius degree. And we observe here that this, again, the results for crude enzymatic extract and partially purified was quite similar. Again, with optimal conditions for both, using 42 units of protease per ml and 60 Celsius degree for both preparations. After that, we studied the influence of the time in the lysis of Xantomonas campestris cells, but using crude protease in this case. And we observed that using these conditions, 42 units per ml and 65 Celsius degree, we obtained almost 40% of increase in transmittance. Based on that, we can conclude that the protease has been partially purified, crude and partially purified presented optimal activities at pH 7.5 and 55 Celsius degree. Both protease preparations showed stability in this pH range, from 5.7 to 9.3. When incubated for 1 hour in the temperature range from 30 to 36 degrees, resulting in 95% of residual activity. And we also observed that both preparations maintain almost 80%, which is pretty considerable, when the preparations were incubated in a higher temperature, like 50 Celsius degree and pH of 7.5. Regarding the clarification of xanthan gum, xanthan gum using this cell lysis of the cells of Xantomonas campestris, we obtained an increase of 20% and 30% of transmittance when using crude and partially purified protease, respectively. The optimum temperature for both preparations for the lysis of Xantomonas campestris cells was superior than 60 Celsius degree, and we obtained an increase of approximately 40% of transmittance when using 42 units of crude proteases and temperature of 65 Celsius degree. These were the main references used in this work. And I'd like to thank you very much.
Obrigada, Fabiano, pela sua apresentação. E agora nós temos mais 5 minutos para perguntas. Pode ser em português, em inglês, né, Fabiano? Fica à vontade. Não temos perguntas. Obrigada, então, Fabiano.